Hi everyone, this is the 8th class. So we will talk about Riemann integral. Okay, first I want to explain a little bit what does that represent. So suppose we have a function. Okay, as you see, and we will care about this interval a, b. Okay, so call this function f. So the integral of f between a and b, so on the interval ab, closed interval ab, represents the area below the curve, below the graph of the function. So this is actually the formal definition of this integral is this sum n to infinity f of x n times, let's call it x sub n, delta x sub n. Okay, so actually this is, maybe we can write like this here. This is better. So here we'll write I to n, okay, x of I, and here we have again I. So what does that mean? Actually, what does that mean? So we know this thing on the left represents the area below the curve, okay? So then this should be exactly representing the same thing. So first of all, it seems we divide the interval AB, closed interval AB, into subintervals. Okay, so let's divide it. So here we have x0 and x1, x2, xn minus 1, and xn, where xn is equal to b. So here we have subintervals. For example, x1, x2 is a subinterval, okay? So we divide them. Then what do? We take some, here I noted that as an endpoint of the of some interval, but we will see that we can take any value from the subinterval. So let's suppose this starts from 0. Okay, so we will take the left endpoints of the subinterval. So for example, so we divided the area, right, into subintervals. Okay, it will continue like this. So what do we do now? We take the left endpoint of each subinterval. So for this subinterval x0, x1, we will take x0. So and take the value at that point of the function. So it will be this point, right? So then what do? We multiply the value by the length of the subinterval. So here we have the length of the subinterval, and we multiply it by the value of the function at x0, which is a. So we obtain something like this, right? We obtain this rectangle. Okay. Then what do? Then we pass to the next value of I, which is 1. So again, we know the length of this subinterval is this, and we multiply it by the value of f at x1 now, because this is the left endpoint of this subinterval. So now what do we have? We have this rectangle. Then we pass to the next value of I, which is 2 now. We started with 0, then 1, then now 2. So we have now this subinterval. Of course, here we have x3. Okay, now we have this subinterval. Then the value of the function at x2, because this is the left endpoint. Okay, as I said before, we can take any value from the subinterval. Okay, here I take always I take the left endpoints. Okay, now what do we have? We have this rectangle too. Okay, so we keep continue like this. Okay, so for the last part, we have this subinterval and this value at xn minus 1. Okay, so we get this. This is just for n many subintervals. Okay, but you know these rectangles are greater than the areas below the curve, right? So if we take the limit when n is approaching infinity, we will obtain exactly the value which is approaching the area. Okay, that's why we take limit. Okay, for some fixed n, we have this. If we take the limit, we will obtain the integral. Okay, that's why the formal definition of integral of Riemann integral, and this is called Riemann sum. Okay, that's why the formal definition we give it like this. Okay, now we can start the worksheet. Here we have the first question. What does it say? We are given this function f of x, 1 plus 2 over 3 x squared, okay? And we're given this interval from 1 to 5, okay? What do? We will compute the Riemann sum, as I noted before, and we will divide this interval into 6 subintervals. And what do we take inside of the function? We will take the sample points to be the left endpoints, as I did before, okay? So we know already what it represents, so we don't need to do something for that. So we need to first find the length of subintervals. So we will obtain at the end the same subintervals. So each of their lengths will be equal to each other. So if we say delta x, if we denote it by delta x, delta means always the distance in mathematics. That's why we denote it by this. Okay. So what do we have? We will just compute the whole length of the given interval, okay, which is 5 minus 1, and we will at the end obtain 6 subintervals. That's why we need to divide it by 6 to get the length of each subinterval. Okay, so here from this computation, we see that each subinterval is of length 2 over 3. Okay, now we need to find the left endpoints of each subinterval to compute the value of f at there. Okay, so what do? First of all, we have 1, right? The interval starts with 1. Okay, so x0 is equal to 1, as we have here. So then what do? We need to compute x1, and we know the length of this subinterval is 2 over 3. So we add 2 over 3 there and get 5 over 3. And then what? To compute x2, we add 2 over 3 again and get 7 over 3. And similarly, we obtain the other values. Okay, so here we have subintervals. and left endpoints. Now we want to compute Riemann sum. We know its formula is given as this. So we start with 0. Why? Because we will get left endpoints. Okay, we will take left endpoints. And for example, the left endpoints of this first subinterval starts with x0. Then it should be 0. Okay, and until 5, because for this last subinterval, we will take x5. Okay, that's why we start with 0 and end with 5. Now we compute this. We know this delta x sub I is equal to 2 over 3, right? Each subinterval is of length 2 over 3. And we can write it outside of the sum because it doesn't depend on I. That's why we can write it outside of the sum. So here we have this. Now what do? We compute the sum. We will first write 0 and we get f of x0. Then plus, as we have sum here, plus when we write I equals to 1, we get f of x1. And when finally we write 5 and get f of x5. So we know each of these xi's, each of these xi's values. So we write them. We know x0 is equal to 1. That's why we computed them. X0 is equal to 1, and we wrote 1 there. And x1 equals to 5 over 3. We write 5 over 3. And similarly, at the end, we have x5 there. So we write the value of x5 and have this. Now, how do we compute the values of the function? We are given the formula of the function, right? So instead of x, we will write, for example, 1, 5 over 3, you know that. So we get this value. Don't interested in with the final number, okay? Just get the idea. So what do we do first? We are given this. We are given this interval, right? 1 and 5. So what do we do first? We divide it into 6 subintervals. Then it says take the left endpoints. That's why after finding the length of each subinterval, we find the left endpoints of each subinterval, okay, till x5. Okay, we have them. Okay, we compute them. Then what do? We compute Riemann sum. So we need to obtain this sum. Okay, and we know this is 2 over 3. So we write it outside of the sum and get the values of f by using its formula, and finally get the value of Riemann sum. Okay, so here what did we do? We divided into 6 subintervals and take the left endpoints to get the rectangle, the areas of rectangles. Okay, and for that, for example, we take the left endpoint and get the area of the rectangle again, and then the other one. Okay, and finally the last one. Okay, so as you can see, this is not exactly the integral of f on this interval 1 and 5. This is not exactly that. This is approaching to that number. Okay, as we take the left hand points, we obtain rectangles which are below the curve, right? That's why we don't have, for example, here we don't have these values, these areas. That's why it is approaching. That's why we need to take limits to get the real value of this integral, okay? And we're given this function sine this plus cosine this. We're given this interval from 0 to 2 pi, and we divide this again. we need to take 6 subintervals. That's why here we have the delta of delta x, okay? Each subinterval should be pi over 3. Now we take sample points as the middle points, okay? So for example, for this interval x0, x1, 0, pi over 3, we need to take the middle point, okay? And for that, 2, okay? For each subinterval, we will find the middle points. How do we do that? For this one, we write pi over 3 minus 0 over 2. So we get this pi over 6. And for this one, we have pi over 3 though, and then x2 minus x1 over 2. We write that, we compute that, and get pi over 2. Okay, we will denote the middle points by using the star, okay, the symbol. So for each subinterval, we get the middle points. Now what do we have? We have this Riemann sum, okay? For this part, we know it is pi over 3, right? Because you can see between pi over 2 and pi over 6, we have pi over 3. We just we had translated them with a distance pi over 3, so we have the same distance. Okay, so again we write it outside of the sum. We start with 0, as I denoted it by x0 star, okay, till 5. So what do we have? The first middle point is pi over 6, we wrote there, and then pi over 2, and then 5 pi over 6, till 11 pi over 6. Okay, so by using the definition of this function, you can find easily the value of the function. At the end, you will obtain 0. Now we're given this graph. We will estimate the integral between 0 and 10, okay, on this interval. First, we will take right endpoints, then left ones, then midpoints, middle points, okay? Now, for each computation, we need to compute the distance, the length of subintervals. So first we note that. So it's 10 minus 0 over 5, as we will obtain 5 subintervals. We divide it by 5 and get 2. So first we have the point 0, because the interval is starting with 0 here. And at the end we will obtain 10, because it ends with 10. And then we add 2 each time. So we have 2, 4, 6, 8. Okay, so we denote them by x0, x1, till x5. Okay, so for this part, we will take right endpoint. So what's the right endpoint of this subinterval? It's 2, right? So we start with x1. That's why we write I equals to 1 there. Till x5 we will compute, so we write 5, and f of xi times delta xi, which is 2, we write it outside of the sum again, and we have this. What's f of x1? x1 is 2 here, so what's f of 2? It's given here on the graph, it's minus 1, right? So we have minus 1. What's f of x2? I mean, what's f of 4? It's 0 there, so we have 0. And by using this graph, you get the values of the function and finally get 6. Now for this part, we will take the left endpoints, and so we need to start with 0 there, okay, till 4, okay, as we take the left endpoints. So again, using the graph, you get the values of the function. For example, f of x0 is f of 0. What's f of 0? It's here. It's 3, 1, 2, 3. It's 3. So f of x1, f of 2 is, as we did there before, now it's minus 1, 0, minus 2, and 2. We don't take f of x5. We have the same. The rest is the same with the previous one. So we get 4. And we take the middle points now. What's the middle point of this interval? It's 1, 3, 5, 7, and 9. So what do we have? We again compute the values of the function by using the graph and get 2. Now we have this table for the function. Okay, we have interval between 10 and 30, as in here. Okay, we know the values of the function at 10, for example, it's minus 11, minus 12. And for example, at the point 14, we have minus 6, okay, as you see. So we read this table as that, like that. So again, we will find this integral, and of course, we will use Riemann sum. So first we take we find the length of the subintervals. Okay, so 30 minus 10 over 5, we get 4, okay? So we divide it by 5 subinterval, okay, as in here. Okay, so we have this. Now we see that f is an increasing function, okay? We will find an estimation, okay? Lower and upper estimations. So we have, it's better if we visualize it. So if you have an increasing function, so suppose you divide it, so suppose you divide it by some subintervals. So if you take, for example, you have x0, x1, x2, and x4. Okay. If you take the left-hand points of the subintervals, what will we get? So for lower, we will compute, we will take left-hand points. Why we take left-hand points, I'm explaining it. So here we have this, and finally this, okay? So we have this this area, the black area, okay? If we take left-hand points, okay? Now let's take right-hand points. Remind that the function is increasing, okay? Now we take right-hand points and get this, right? Because the value of the function will be something like this there, okay? That's why we have this rectangles, okay? As we have here. Okay, so you see the upper bound, we will get the upper bound, the upper estimation if we take right-hand points. And if we choose left-hand points as sample points, we will get lower estimations because the black area is less than the green one, okay? This is because, of course, the function is increasing, okay? Because when x is greater than the previous one, the function's value will be greater than the previous one. That's why we have the greater area before, if we compare with the previous one. Okay, so for lower estimate, we take left-hand points. Okay, as you see here, we start with 10 till 26. Okay, as we know the value of the functions, we wrote them. Okay, as the x sub I is 4, we wrote it outside of the sum, and get this. Now, what about the upper one? Now, for upper one, we compute, we take right endpoints till 30. Okay, I wrote for lower black there. Now I wrote black again, but for upper, sorry about that. but you get the point. So okay, now for that part, what did we do? We take right endpoints, 14, 18, 30 till 30. So we get 16 here, right? As you see, we have first for lower estimate, we get something negative, and for upper, we get something positive. This is greater than the previous one. That's why this is upper estimate, okay? Now, we will express these limits, okay, as integral. So you remind the formal definition. So this is, we see on pi and 2 pi. That's why we write pi and 2 pi there. Okay, this is the boundaries of the interval. Now, what's the function? Here we have x sub I, x sub I there. So f of x should be cosine x over x dx as in the formal definition of the integral. So this is delta x, this is dx, okay? Both means the small difference on the axis, okay? So here we have the integral. Now for this part, we have 2 and 7 there. Now what's the function? 5x to the 3 minus 4x dx, of course. Now we will use the formal definition of the integral to compute this. So remind the definition of the integral. Okay, we know this. Okay, so at the end we will see some sums like this. That's why I noted first them. Okay, so delta x will be, we have this interval -2 till 0. So we have 0 minus 2 over n, we get 2 over n. So we see n as some fixed number, okay? Okay, it's so easy, don't be confused. So here we have the limit of this sum. Okay, as always we write it. This is the formal definition, so there is nothing complex here. So what do we do now? We have x sub I. We have x0 is equal to -2 here. Okay, then x1 is -2 plus 2 over n, as in here. Then xi should be -2 plus 2 over n times I, because we will add 2 over n I times. That's why we have this. So instead of xi, we will write that and get this times 2 over n, which is delta xi, which is delta x sub I, okay? So we write it outside of the sum, but not outside of the limit, because we have here n, okay? Be careful about it. Then what do we have? We have this. How do we obtain it? We know the function's formula is x squared plus x. So instead of x, we write -x plus 2 over ni, okay? So here we have this. Now we make some computations. You can do that by yourself, or you can read that by yourself. There's nothing complex there. So here we obtain these sums. Now we know I squared, the sum of I squared is given by this formula, as I noted before. Okay, so and the sum of this is this, n times n plus 1 over 2. And this we add 2 n times, okay? So it is clearly 2n, okay? Now what do we have? We multiply 2 over n by we distribute it into the parentheses, so we get this. Now when n is approaching infinity, you know how to compute the limit. We see each of the fractions has a limit, so we separate them and get the values for the limit and have this sum, okay, 2 over 3. So you can stop the video and read again the computations, okay? So now we are given this integral. Again, what's the interval we're given? It's between 1 and 4. So here we have 3 over n. So each subinterval should be of length 3 over n. Now xi is equal to 1 plus, because why do we have 1 here? Because the interval starts with 1. So here we have x sub I. Okay. Now what do? We use the formal definition again. And into the f, we write 1 plus 3i over n, as xi is that. Now, again, we write delta x sub I outside of the sum, but not outside of the limits, okay, as we have here n. So what do we have? We use the definition of the function again to get this value. So clearly we plug x equals to 1 plus 3i over n here. Okay, we get this and make some computations and get this sum. We again know I squared, the sum of I squared is given by this formula and I given by this formula. We add minus n many times and get minus n, of course. So we distribute this 3 over n into the parentheses and get this, and by taking limit you get this minus 3. Again, we will use the formal definition to get this equality. So we will show some equality. That's why we start with the left of the equality and try to obtain the right one. You can also, if you need to show some equality, you can, for example, show the difference of them is equal to 0, or you can start by left and get the, by right and get the left one. For that one, we start with this integral because we know the definition of that, the formal definition, okay, and try to get that. So each subinterval should be of length this, okay, and we write xi like this because the interval starts with a, that's why we write a plus da da da, okay. We know delta x is this, so we multiply I by this distance. Now, what do we have? We have the formal definition. We write delta x sub I outside of the sum, b minus a over n. And we have here xi is this, that's why we write there. And we use the definition of the function, which is f of x is equal to x, right? So we write exactly the inside sum outside of the function because f of x equals to x. So if we write a plus b minus a over ni instead of x, we get the same. So what do we have? We have this sum plus this sum. This will give us n times a, sorry, and this will give us, here we have I, remember, this will give us that, and we have this multiple b minus a over n. We multiply by this sum and get this value, okay. When n is approaching infinity, here we have some constant number, it does not depend on n, that's why we have the same, okay. And this is dependent on n, so we take the limit of that and get this value. And finally, we make some computation and get this as in the right-hand side of the equality. So we started with this one and show that. Now, we will evaluate with E here. So this limit, again, we will find the length. So we have 2 pi minus 0 over n. We have 2 pi over n. And xi is 0 plus 2 pi over n times I. So we have 2 pi over n times I. Now we compute this by using the formal definition. And delta x is 2 pi over n. There we computed. And this is equal to that. Why? Because f of x is defined by this x squared times sinus x. So instead of x, we write xi, which is 2 pi over n times I. So here we have this. We don't evaluate the limit, as it says. We have just this equality. Now we will compute the integral, not by using the formal definition, but geometrically we will compute it. Okay, so what's the integral of g, whose graph is this? From 0 to 2. So from 0 to 2. So it means, you know, the area below the graph. So we need to compute the area below the graph of graph of G. So we need to compute the area of this triangle. So it's, you know, from high school or, I don't know, primary school. So, you know, 4 times 2 over 2, you get 4. Okay, what about this? From 2 to 6. From 2 to 6. Now, what's the area of this semicircle? It's pi 2 squared, right? Because the radius of the circle is 2, right? Over 2, because we have semicircle. Now we have 2 pi. From 0 to 7, so this is some property of the integral. So you can compute this by, so suppose we have this, okay? Not with the equalities, it's no meaning. So suppose we have this and we want to compute that. You can also compute this one. Okay? You can separate the interval. Okay, as we did always. Actually, this is coming from the definition, the formal definition. It's no big deal. So for this one, from 0 to 7, we can separate it from 0 to 2 plus from 2 to 6 plus from 6 to 7. Okay. Before we computed them as in the previous part, so we have this one, these ones, and for this we have this triangle, little triangle. So it's 1 over 2. Okay. So at the end we have this. Okay. Okay, we will again geometrically find the areas. So we want to compute this integral, okay, from -1 to 2. So what do we have? We have this triangle and this one. So 1 over 2 for that part, and this for this part. We have this, so okay. And for this, we can separate it as I said before. But now it's not about separating the interval, but this. If we have this, we can write f plus g. Okay, we use this here. Okay, so here it is the constant function from -3 to 0. So we get this area, right? Here we have, which is 3. As I did there, it's 3. So what about the second one? This is, if we equalize it to y and take squares, we get this, okay? So this is the circle centered at the origin and whose radius is 3, okay? As we have this interval from -3 to 0, we have only this quarter circle. So the area of this is 3 squared times pi, and we have this part only. We divide it by 4 and get this part. So finally we have 3 plus this, 9 pi over 4. So it's so easy. So we have the interval, not the interval, only a point pi as we have endpoints. So what's it? It's 0, of course. Okay, as we have only 1 point. So what about this? We rewrite this given sum. Okay. So instead of that, we separate it from -2 to -1, and from -1 to 2. Here we have. So this sum. So this sum is equal to that. Okay. And we have this, exactly the same things. So what do we have now? We have minus in this integral from -2 to -1, and this integral. So here we have 0, okay? And the rest is this. And this is from -1 to 2 to 5. So we can write it as only in one integral, okay? So this is equal to this integral. Now we are given this function. It's defined by 3 if x is less than 3, and it's defined by x if x is greater than or equal to 3. Okay, we compute this. We can separate it as in these intervals into 2 intervals, subintervals, from 0 to 3, from 3 to 5, because we separate this integral by using its domain. Okay. So when x is greater than 3 or less than 3, the definition of the function change. That's why we separate it. So when we have this interval from 0 to 3, we're here. So it's defined by 3. And for this interval, it's defined by x. So here we have these integrals. Now what do we have for that? We take the integral. So we use the rules, okay, you should know them. We multiply it by x from 0 to 3, and here we have x to the 2 over 2. Okay, so you should know that these are so basic. If you have this integral, it's computed by this. Okay, if you have in general this, it is computed by this. And if you have, for example, e to the x, it's e to the x. Well, we will see them in the previous, in the next question, so I don't write them. So what do? We write x equals to 3 first, then 0, and subtract them. For that, we do the same things and get 17. Now we compare these integrals. So it's clear that c is greater than d. Here we have c. It's greater than d because it starts with 4 and this starts with 3. So it will be greater than d because the area we compute here starts with 3. It will be bigger than that. So d is greater than a because it starts with 0, I guess. Okay, so here we have. Now we see that b is less than a. And most importantly, b is less than 0. It's from 0 to 3. From 0 to 3, it will be negative because it is under the x-axis. Okay, so it's less than 0. And a, it starts with exactly 0 to 3, and it will be greater than a. That's because if we subtract this area from that, we will have something positive, so it will be positive, and by using these two inequalities we get this. Okay, now we're given this function g as an integral. So g of x is defined by this integral from 0 to x. Okay, and the graph of f is this. Now we evaluate g for these variables. Now, for example, g of 0, from 0 to 0 by definition of g, we have this integral. It's of course 0. And g of 1, it's this integral, right? So we call that this is the graph of f. Okay, from 0 to 1, we have this triangle, so we have 1 over 2. From 0 to 2, we have from 0 to 2, we have, of course, 0. And from 0 to 3, we have g over 2, as we computed before here, plus from 2 to 3, which is this. So it is minus 1 over 2. And we compute it like this. Here, geometrically, you can find all values of g by using this graph. Okay, it's easy. We did that before. What about g of 7? We will estimate it. So we estimate g of 7. We know it's from 0 to 7 here. Okay, it can be written as we did there before, g of 6 plus this. What's g of 6? We computed it before. It's 4 plus this integral. So from 6 to 7. Here we have curve, right? It's not triangle. So it will be approaching the area of the triangle, will be approaching the area of the area below the curve. Okay, so we compute the area of the triangle and we write it like this. It means this thing here, this sum, is approaching to this number. Okay. Now, for the last part, for C, we find the max and min values of the function g. So here you see the values, okay? It gets minus 1 over 2 when we put 3, so the minimum value at x equals to 3, and maximum value is, here we have, x equals to 7. And we sketch the graph of g. Of course, we cannot sketch the exact graph of g, but we make some estimation. So when we put 0, we get 0. Here we have 0. When we put 1, we have 1 over 2, as in here. When we put 2, we get 0 again, here. So we continue like this till 6, okay? All are lines, okay? All of them lines. But from 6 to 7, here we have some curve, right? It cannot be a line. So it will be some curve, right? So from 4, because the value of g at 6 is 4, from to 11 over 2, okay? At 7, it's approaching to this number. So here we have. We have some recalls, the fundamental theorem of calculus. So we have two parts of this theorem. Okay, you can read them by yourself. So we're given this function. We will find g prime by using both of the parts. Okay. So if we use the first part, okay, the first part of the question says use the first part of the theorem. So we use it. And we see the assumptions in the theorem hold because 2 plus sinus x is continuous on this interval because sinus is continuous everywhere and 2 is a constant function and the sum will be again continuous. Okay, so we use the first part and get g prime should be equal to this one's derivative, okay, and it is equal to this because it says g prime of x is equal to f of x. If we have this is x, okay, from a to x. So here we have this. So if we use the second part, we need to find an antiderivative of the function, which is this function satisfying this equality. The derivative of the antiderivative gives you the real function. Okay, so what's the antiderivative of this 2 plus sinus t? It's 2t minus cosinus t. Okay, you just basically take the derivative. So this is the antiderivative of the integrand. And from 0 to x, so you put first x, then 0, and get this value. What's the derivative of this function? It's 2 plus sinus x, as we computed in the previous part. Okay. Again, we find the derivative. We use the first part of the fundamental theorem and get this. So you have this function 2 plus t to the fourth. And what's f of x? We just plug t equals to x, okay, to find the derivative. And for this, we have some constant to apply the theorem. We need to have some constant below and x above, okay? So here we have some constant above. Now we can write it again, some property of integral. You should know this one too. If you have some function, you can rewrite it like this. Of course, it's the same with this. Okay, this is the property that we use here. Okay, so here we have this function. You can think of it here, is that minus. Okay, so the function is this minus cosinus square root of t. Instead of t, we plug x and get this. So g prime is this. Now for this, we don't have some variable x. We have a function sinus of x, right? Now for that, we need to make some substitution, which is so easy, don't be afraid. So we plug u equal, we write u equals to sinus x, and we differentiate it and get du equals to cosinus x dx, okay? We just take derivatives. Okay, so we have here this part. Now, we have this function. We rewrite that. The aim of these things is to get something like that. Below, we need to have some constant and above some variable, okay? So, we rewrite, so our aim is to compute the derivative of y with respect to x. But now, instead of x, we wrote u. That's why this is exactly the same with this. dy over du, du over dx, okay? It's the same. So here we have du over dx. From that part, we get its cosinus x. So du over dx is cosinus x. And the only thing we need to compute is this derivative, okay? So here we rewrite again, because here we have u and above we have constants. We rewrite again. Here we have minus, as I said before, the property that we used. So what do we have now? We take the derivative. Now we can use the fundamental theorem and have this. Instead of t, we write u, because here we have u, okay? Now, but we're given the function as in terms of x. That's why we rewrite this function by using this equality, okay, there. U equals to sinus x. Instead of u, we write sinus x. So here we have this. Okay, now we evaluate the integrals. So this is so easy, but pi x from -5 to 5, right? So 5 pi minus 5 pi, which is 5 pi, so we get 10 pi. Okay, what about this? We write +1 over the same, right? From 1 to 8. You make the computation, it's not important. The important thing is to know this equality, okay? The rest is easy. So for this part, we don't know how to integrate the division, right? So we rewrite it. So here we have x minus 1 over x to the 1 over 2. We rewrite it as in this form because this is equal to x over this minus 1 over this, right? So we rewrite it. Here we have this function. Now how do we compute it? We know that as we did there before, we know it. So here we have this function from 1 to 9. We just plug x equals to 9, then x equals to 1, and subtract them and get this value. Now, if we have, let's suppose we have some function in terms of x, okay? This is u of x. U of x is some functions like sinus x, cosinus x, or something like this. A function in terms of x, okay? The important thing is this. So how do we compute this integral? It's the same u of x over u prime of x. Of course, the derivative of u with respect to x, okay? So here we have e to the z over 2. We write e to the z over 2 over the derivative of this function with respect to z, right? So we have 1 over 2. Here we have z, that's why we integrate with respect to z, okay? So here we have this from 1 to 3. We just write the rest, as you know. So what about this? This integral, this one's integral, is ln of x, okay? You should know this and this. So we have 4 ln of x from 1 to 4. We write it, and we know ln of 1 is equal to 0, okay? So here we have this. We can write instead of 4, 2 to the 2. So we can write this one here as a multiple. So here we have 8 ln of 2, okay? You don't have to do this last equality, the last operation. You can leave it like this. So we need to take this one's integral. We know the derivative of second function is this, okay? So the integral should be equal to second theta from 0 to pi over 4. Okay, we plug pi over 4, 0, and subtract them and get this. Now we're given this function. Again, it's defined piecewise, right? So we separate the given intervals from 0 to pi. We separate it like this because of this definition. So here on this interval we have sinus x, on there we have cosine x, and what's the integral of sine x is minus cosine x from 0 to pi over 2, and this one's integral is sinus x from pi over 2 to pi, and you compute the rest, it's 0 you get. Now we want to find the derivative of this function. Again, it starts with tangent x to x squared, okay? Here we need to do something again. So we can separate it by using some a, some constant a, okay? Here we think a like this, okay? Okay, this may come to you some weird thing, but it is. It's mathematics, so what do we do here? We need to write it, write this constant below. So we rewrite it with multiplying by minus, okay? So here we have a from 2 x squared, okay? we don't do anything here because the constant is below. So for this part, we use substitution again. Okay, and for this part, we use this substitution. Here we have x squared, okay? So g prime is dg over dx, of course, d over du, here, d over du, okay, times du over dx, plus d over dv, because this is coming from this. So dg, du, d over dx, plus dg over dv, dv over dx, okay? So we know du over dx by just differentiating it, okay? It is this, and dv over dx is this 2x, okay? Just differentiate them, okay? You'll get that. So what about these parts? We see we have u here, okay? We plug t equals to u there. And here we have v, we plug again, t equals to v, okay? Now what do we have? Of course, we need to obtain something in terms of x. So instead of u, we write tangent x, and instead of v, we write x squared, okay? This is homework for you. It's easy, okay? If you cannot find the answer, you can ask me on office hour, which is on Friday between 5-7 p.m. Okay, I guess these are the last problems. So here we're given these two functions. Okay, we will find g2 prime. Now first remark that g prime is f of y just by using the fundamental theorem. And if we take again the derivative, g2 prime will be f prime. Okay, so we need to compute this f prime. Here we have f. Okay, again we have sinus x, we make substitution. Okay, we have this. I hope you get that part till here. So for this part we have this, and du over dx is equal to cosine x. Instead of u, we write sinus x, so we get sine squared there. Okay, so g prime is f prime. So here we have f prime of x. Instead of x, we write y and get this. Now we need to compute the value of g2 prime at pi over 6. Instead of y, we write pi over 6 and get this. The computational part is easy, so. Now we need to find some function f which satisfies this, okay? Now if a function satisfies this, then we need to have, if we take the derivative, we need to have this, okay? Now what's the derivative of that? It's f of x over x squared, and the derivative of this is 1 over square root of x. We apply here the fundamental theorem, okay? So what's the assumption of the fundamental theorem? You need to have some constant here and some variable here, and remind that the function inside of the integral should be continuous. But this function, f of t over t squared, is not continuous on 0, because if t equals to 0, we have something undefined, okay? So that's why if we choose a is greater than 0, then this function will be defined on some interval which does not contain 0, okay? So the number a should be greater than 0. Then we can find some function satisfying this equality, okay? So that was the last problem. As I said before, you can attend the office hours to ask your questions. It's on Friday, so hope you see you there. Take care.